So thus far we introduced organic chemistry, we looked at the different ways one can depict organic compounds, and then I started moving to the alkanes, talking about naming alkanes, straight chain and branched alkanes, talked about the different structural isomers associated with alkanes. Now it's time to talk about alkanes as actual compounds. Alkanes form a homologous series. Homologous series is, I hope, a word you remember from GCSE or before. That is a series of compounds that have similar properties and a general formula. Now I'm going to talk about the general formula of alkanes now, and each time we introduce a new functional group, I'll talk about how the general formula associated with that different functional group can be derived from the general formula of the alkanes. Right now then, let's just worry about the general formula of the alkanes. Hope you see as we go 1, 2, 3, 4, 5, 6 and so on in terms of the number of carbons, not just as the number of carbons increase by 1, as you would expect as I'm going in order of increasing carbons, but the number of hydrogens increases by 2. So for every extra carbon, you have 2 extra hydrogens. And then, of course, when we start off with methane, CH4, right, well, there's 1 carbon atom. So 1 times 2 is 2. There are already 2 there with the CH4. So our homologous series is CnH2n plus 2. Let's just illustrate that if you didn't get my rather fast derivation of it. For example, butane. Butane, you've got 4 carbons. 4 times 2 is 8, plus 2 is 10. Okay, with each increase in carbon atom, you get twice the increase in hydrogens. 2 hydrogens for every carbon. Now, one of the times you might have seen alkanes even before doing organic chemistry was when you were looking at intermolecular forces, because the alkanes, being a homologous series, are a wonderful example of how dispersion forces change within a series of similar compounds. Okay, if we just look qualitatively, methane and ethane are gases at room temperature. In other words, they've boiled well before you get to room temperature. Propane and butane are also gases at room temperature, but they're so-called liquefiable gases. If you increase the pressure a little bit at room temperature, then you can turn them into liquids. And then pentane, hexane, heptane, octane, and so forth are liquids at room temperature anyway. If we list out the melting and the boiling points, we can see that the boiling points increase nicely. Minus 162, minus 89, those are the 2 non-liquefiable gases. Minus 42 and 0, particularly butane at 0, don't have to increase the pressure on it too much to turn it into a liquid. You don't see it so much over here, but in the States, when you went out into the country, you would see large tanks outside people's houses, and these contain propane under a reasonable amount of pressure so that they would have gas on hand to fire their gas stoves, their gas heating, and so forth. Okay, back in the days when people were very silly and smoked, and you had cigarette lighters, you would fill those cigarette lighters with lighter fluid that was liquefied butane, so butane under a little bit of pressure. So if you actually looked inside a lighter, a lot of them had transparent sides. You could see this liquid in there, but when you opened it up, you get the hiss of escaping gases as the butane vaporized when you opened it up to atmospheric pressure. Anyway, then pentane, blah, 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 all liquids, as we said, and you could again see that the boiling point increasing nicely. Okay, melting point, same idea, with a strange exception of propane that I can't explain it right now. I had a fast look to see if anyone had explained it and couldn't really find it. But anyway, generally melting points again increase as the number of carbons increases, thus your molecules are getting bigger. Another physical property of note is the density. The ones in pink are the gases, and of course gas densities we express as grams per cubic decimeter or grams per litre, and of course, as you would expect, as the molar mass increases, so does the density, because the density of gases is directly proportional to the molar mass of the gas. But then when we get to the liquids, you can see again they're increasing as the alkanes get heavier, but they're all less than 1, which means that all of these alkanes float on water. And of course, you're familiar with that idea when you look at petrol, for example, which is made up of heptanes, octanes, and various other things. It floats on water. If you spill a little bit of petrol on a puddle, it floats on top and you get that lovely iridescent sheen.